Hello everyone, this is Elisa Baum. I am Percona's Director of Product Marketing. We will begin in just a moment, but first I'd like to conduct just a bit of housekeeping. If you could please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me, that would be really appreciated. And let me check. Great, I see hands. Thank you very much. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on Percona's MySQL performance blog. In addition, a recording of this webinar and the slides will be made available to everyone within 48 hours. With that, I'd like to thank you for attending today's webinar. Percona and TokuDB, Architecture, Design, and Practical Benefits, is being jointly presented by Peter Zaitsev, who is Percona's CEO, and by John Tobin, who is a Senior Systems Engineer at Tokutek. And with that said, I will turn the floor over to John. Go ahead, John.
Thanks, Lisa. Good morning, afternoon, or evening to everybody that's on the phone. As Lisa said, my name is John Tobin. I am the lead sales engineer or senior systems engineer, however you like to say it, at Tokutek. So for people who don't know who Tokutek is as a company, we're the company that invented Fractal Tree Indexing back in roughly about the 2007-2006 time frame. But what we decided to do is, instead of making people actually learn a new database and re-platform in order to use the Fractal Tree, we decided, why don't we just put it into existing technologies? And the first one was TokuDB, right? We created TokuDB for MySQL so that people could use the Fractal Tree in their MySQL environments without having to change their application code. Already having known a good database, a solid database like MySQL, we figured we'll create a storage engine for MySQL called TokuDB. Recently, we also created a product called TokuMX, which is an actual distribution of MongoDB. So you could think of it as a fork, and it runs just like MongoDB does as well. And you know, we were started by a couple of professors who did research at MIT, Rutgers, and Stony Brook. And as I said, the Fractal Tree Index is really the solid base of what we do. But we also have some great engineers on board that have done some other things that I'll go into some detail about in later slides today. But to start off the conversation, I just want to tell you a little bit about traditional indexing technologies. And the one that's used most widely is called the B tree. And the B tree was invented, or at least theorized, back in the early 70s. I think it was 72, but you could double check me on Wikipedia about that. And really, it was invented in a time when big data was really an IBM storage array that contained probably roughly about 1.4 gigabytes worth of data and probably cost about $500,000. So it was invented in a time when the world looked a little bit different from an IT perspective. But that being said, the B tree is an awesome piece of technology and an awesome piece of research. And the reason is that it can ingest data very quickly and efficiently, and it can also store it in a way that's easy to search, in a way that's easy to query. So it can get data in quick, and it can also put it down in a format where it's easy to get back out, which was revolutionary for the day, and is still pretty revolutionary today, considering it's used in a lot of databases, not just in ODB and EnergyBe for MySQL, but also in Oracle, also in Microsoft SQL Server, and you know, it's used in many non-relational databases as well. So don't think of it necessarily as outdated. It really is good at what it does, and I'll go through what it does good in this. But let's talk a little bit about what it looks like, what the structure of it looks like. If you look at this slide, you'll see that there are a bunch of different boxes, and those all represent nodes in the tree. Some are internal nodes, like the top, which is the actual head of the tree itself, and then there are also internal nodes which all contain a path to the data. And I'll show you some example of what this looks like. But you also have pivots in there as well, which are represented by basically the values in the box, and you also have pointers which give you a path down to the data. And down at the very bottom of the structure itself, you have leaf nodes, which contain the actual data in the tree. So all of the data that's interesting to you is contained down in those leaf nodes at the very bottom of the tree. And that's all contained in sorted order, right? So let's take a look at what this actually looks like. So in a very simple use case, we can insert 15 down into the leaf nodes. And so what you have is a pivot rule, which down the bottom you can see is greater than or equal to. So what that means is that once I come to one of these nodes and I look at the value in it, if it's greater than or equal to, I will go to the right. If it's less than, then I'll go to the left. So we want to insert 15. First we come to the head of the tree, we see 22. 15 is less than 22, so we go to the left. At the next node, we hit 10, right? 15 is greater than 10, so we go to the right, and we insert 15 in sorted order in between 10 and 20. So that's kind of the magic of the insert in the tree. Gets data in there fast, but also in a sorted order where it's easy to get out. So now let's look at what it takes to do a query. And so we're going to use the same pivot rule. So we want to find 25. We go to the right of 22 where we hit 99. 25 is less than 99. We go to the left. We hit 25, sorted order down the leaf node. So these are very simple use cases, but this is what the B tree does really well. But there's a problem here. What the problem is that the data structure itself can only reside in RAM for so long. Eventually it's going to get larger than RAM, and you have to do some sort of balancing act to try to figure out what data is going to sit in RAM where I can access data extremely fast, right? Accessing data from RAM is about the fastest way that you could possibly access data in a computer. And so I'm constantly trying to do this balancing act where I'm figuring out what's going to fit in RAM and what's not going to fit in RAM. And remember, all the data that you need is down in the leaf nodes. And at some point, those leaf nodes are going to sit down on disk. And for every database operation in the B tree, you always have to traverse for inserts and updates down to the leaf nodes to be able to page things back in memory if they're not already in memory. And so what that means is that your database is actually only going to go as fast as your disks can provide it information. And this is the traditional scaling problem that most people that use a B tree come to. They usually have to either provide more disks, so expand their RAID sets so they can get more performance, or buy faster disks, maybe go to Fusion IO cards and spend a lot of money there so that their database can go faster. What our founders said is there's got to be a better way of doing this. Could we get better software just to do things more efficiently inside the server? They thought yes, and so that's where the Fractal Tree came from. But let me give you an idea of what it actually looks like to be bottlenecked by disk. And so this is a test that I did in AWS, right? And what it is I did a load of 200 million rows into a MySQL database. And what I did, in one case I used what's called provisioned I/O for the volumes in AWS. And what that gives you is dedicated bandwidth, right? It's dedicated storage performance, by the way, that you have to pay for. And it's actually quite expensive. It actually more than doubled the cost of my virtual instance over the course of this test. And I also did it without provisioned I/O, so just a normal AWS volume. And what that gives you is bandwidth and performance when AWS can afford to give it to you, kind of. So basically what I'm creating is a disk bottleneck, but on Amazon standards, not doing it officially. And so the outcome of this, as you can see, unfortunately this is in seconds, but really what it is a 6-time multiplier in between doing it with provisioned I/O and doing it with unprovisioned I/O. It took 6 times longer to do it with unprovisioned I/O in AWS, right? So you have to pay if you want faster. database performance, and that's just due to the disks because memory management is so difficult. But let's look at the Fractal Tree, and let me tell you a little bit about what's different in there. Really, it's more similar than it is different. And the Fractal Tree is pretty simple. If you're looking at the tree and you ignore those green boxes, it looks a lot like what I showed you the B tree looks like. It's a bunch of internal nodes with leaf nodes where you store the data. But what's different is those green boxes. And what they represent is a thing we like to call a message buffer. And so what we do with database operations is we convert them into messages and we drop them into the buffers. And as the buffers build up, they overflow and they split and cascade down the tree, right? And so what we get is a write amortization effect, where database operations build up in the tree, and then eventually, before they get down to the leaf nodes, which will be lying down on disk, they get compressed and they get pushed down to the disk. What this does is allow us to do inserts and updates at cache speeds all the time because of the way the Fractal Tree works. So what's similar to B trees is really the structure, in that we store data in the leaf nodes, and that we also use our indexes for key ordering. What that means is that a primary key in NODB and a primary key in TokuDB are the same thing. Really, it's one clustered index. So you have the index fields that you define for the primary key, and then you have the rest of the data of the row clustered after that. And we do the same thing. We both use clustered primary keys. What's different than B trees is this idea of message buffers, that write amortization effect that I was talking about. And also what's different is the size of the nodes that we use, basically down to leaf. NODB and EnergyBe use 16K, 16 kilobytes, that is, as their leaf nodes. We use 4 megabytes, right? The reason why 16K has to be used, or a smaller block size like that in the B tree, is because we do have to go to disk often. So using a large amount of data for that basement node doesn't make sense, because it will actually take longer for us to fetch that data all the time. But with the write amortization effect that we have in the Fractal Tree, it makes sense to use large nodes like that. That allows us to store data down in large contiguous chunks on disk. It's great, actually, for spinning disks, because when you put contiguous chunks down on spinning disk, you can grab a big chunk of data contiguously on disk very cheaply. That's what spinning disks do great. They have good bandwidth. If you want to think of a Fractal Tree in terms of something that you already know, think of it like a champagne waterfall, where you stack a pyramid of champagne glasses, and you pour champagne in the top, and eventually it cascades down all the glasses and fills them all up. That's kind of what the Fractal Tree does with data, right? If you wanted to think of the champagne like the data, that's basically what you're getting, and the glasses are kind of like message buffers, all right? And eventually the data gets down to the bottom, we compress it and write it down. But if you want to just throw some sample data in there, it looks a lot like the B tree. It looks just like the B tree, except for the message buffers, and the fact that those leaf nodes are actually quite a bit wider than they would be in the B tree. But let's take a look at what happens when we insert, and let's just say 15. So what happens is the database says to TokuDB, let's insert 15. And so what we do is we convert it into a message, and we drop it into that very top message buffer itself. And that's where it sits until more database operations come up, and then eventually they'll build up, they'll split, and they'll cascade down. In search operations, they must actually consider messages along the way, right? Now, a query can't come in and just bypass insert 15. It has to go down and search through the message buffers as it goes down the tree. And so therefore, you're not actually missing any data. You have to actually consider all of those messages on the way down the tree. As the messages cascade down the tree, the buffers will fill up. Like I said, they'll split and they'll cascade down as many levels as you have. This is a very shallow tree. Normally they're not this shallow, so you have many buffers on the way down. That allows you to amortize the cost of more I/O and to build up more data as you go out. And eventually, they'll get above the leaf nodes. We'll take the data, once that leaf node fills up, we'll compress it, and we'll write it down to disk. But what we're writing down to disk is really hundreds or thousands of database operations for every I/O that we push down to disk in those large chunks. That's what gives us such fast update and insert performance. Now, some of you are probably thinking, well, there's a problem here. Now we have a bunch of data sitting in the cache inside this Fractal tree, and what happens if something catastrophic happens and our server suddenly reboots or it crashes? Aren't we going to lose that data? No. The answer to that question is no. You're not going to lose that data. And the reason is because we're a transactional storage engine. We're actually logging all of these for replay. Right? We're not going to let that data go without being written down to disk. So we're actually capturing all those in a log for replay should it crash. Also, what we have is the idea of checkpointing. So we allow you to define the interval, but by default, every 60 seconds, everything that's dirty in that cache table that hasn't been written down to disk is basically cloned and pushed down to disk so that it's durable. What that allows us to do is actually have a copy of data every 60 seconds, so we're constantly not building up. And it also allows us to roll out the old logs. So once we have, more than basically 2 minutes worth of data, we can roll out those old logs and make sure we're not constantly building up logs. So it's basically a maintenance operation to make sure not only we have durable data, but we can also roll out old logs so they're not building up on your disks. So the idea of this slide is that many different things can be messages. It's not just an insert. But we can also do a hot schema change on the database without having to do the background table copy that's usually required in MySQL. Because now in MySQL you can actually change the schema of your table, but really what happens behind the scenes is that we are copying the table and mutating the schema of that table to look like it has another row, let's say. But with the Fractal tree we can convert an actual column addition into a message into it. So in here you're looking at an add column, that very top operation. Let's add a column C4. It's a big int, right? And we insert a bunch of those messages in the tree. And basically what the messages say is that, all right, this row has another attribute, it has another field on it now. It's C4 and it's a big int, so go ahead and use it. And if we go in there and we try to insert into that column, right away we'll be able to use that. Basically all we have to do is take a very quick table lock that MySQL requires, and then we can move on. We'll inject those messages into the tree and they're available for use for you. We can also do things like delete operations, where we can delete values sitting down the leaf nodes or maybe built up in the cache. And we can also do updates. And here you see an increment, so we're going to increment 22 by 5. So now we're saying to the database, or the database is saying to us, 22 is now 27. And we can insert those in the tree, and like I said, the queries have to consider those messages on the way down the tree. Let's talk a little bit about some of the benefits and features, because I've talked a little bit high level about how the Fractal tree works. But we're a transactional storage engine. Right? We're transactional just like NODB is. We're ACID compliant, so you can do basically a multi-statement transaction to the database itself. You can commit that or you can roll back. You commit it, we'll log it. And like I said, every 60 seconds the tree will be checkpointed so your data is durable. We also do MVCC reads, so you're reading a consistent snapshot of your data at any one time. We have compression too, right? Our compression is a little bit different than NODB's compression in that there's a lot less overhead. And Pierre will be talking about that a little bit later on. But basically what we did is when we theorized the Fractal tree and went to implement it, we realized, hey, compression can be had in this scheme without actually having to add any latency to the database. So now because we're already building up writes in the database, right, as soon as we drop them into the message buffer, we acknowledge back to the database and say, hey, we got the data. Go ahead and move on. What we're going to do is we're going to amortize it as it flows down that champagne waterfall. And right before we get to those leaf nodes, we're going to compress it and write it down. Therefore, we're not actually adding any latency to the database there. We're just able to take the data, compress it, and write it down. And we allow you to pick any of 3 libraries depending on what ratio you like. If say the size of data is the most important to you. You want the data to be the smallest it can be on disk. Use LZMA. That's the heaviest weight compression library. Will get your data the smallest. But it also has CPU trade-offs. And also, don't forget, on a query, we may have to read data up from disk. And decompressing that data is going to add some latency. We also have the zlib library, which is our default. It offers a pretty good compression ratio and is a little bit less CPU taxing. And we also have QuickLZ, which is the lightest weight compression. So your data will be a little bit bigger on disk, but it doesn't really use too much in terms of CPU. It also adds the least amount of latency in most cases. Moving on, you already heard me talk about hot schema change, but there's no table required, no table copy required in the background. That means, no additional CPU resources, no additional memory resources, and it also doesn't take up the amount of disk to hold 2 copies temporarily. And what it'll allow you to do is to add a column, to drop a column, or to expand things like var binaries, var chars, and things of that nature. You can find all of that in our documentation. But now you kind of have the ability to use MySQL a little bit more like some of the NoSQL technologies, right? You have a little bit more agility built into your database. The next thing is clustered secondary indexes. I talked a little bit about clustered primary indexes, and I talked about how InnoDB and TokuDB do it the exact same way. We have a clustered primary index. What a clustered secondary index is really the ability for you to make a secondary index with different fields in it, just like the primary index. So if you wanted to reorder your data on another field, because you query very often maybe the entire row based on another field that's not your primary key, you can do that now. Whereas in InnoDB, you can only use a covering index. Right? In TokuDB, you can choose, I want to do a covering index, but maybe I want to reorder all my data and do a clustered secondary index. The drawback to a clustered secondary index is that you're going to store a whole other copy of the data. However, if you only want to define one extra clustered secondary index and you're getting the benefits of compression, you usually actually win out over your disk footprint with something like InnoDB anyways. The reason is the compression ratio is usually so deep that adding another copy of the data is really still going to be a win. You'll still be maybe 10% smaller on disk, maybe even more than that. Read-free replication. This is an interesting one that we actually developed for a customer of ours not very long ago. It's been out for maybe about 2 months now. What read-free replication is basically on your secondaries. With MySQL replication right now, there's always a read before write nature. And basically what MySQL is trying to do is guarantee that the before image of the row on the secondary and the before image of the row on the master look the same before it applies updates to the secondary. So it's always trying to tell whether or not I'm working from a good copy of the data. So basically, if you're using row-based replication with TokuDB, and you guarantee us that the data on your secondary is the same as the data on your master, and you can turn your secondary into a read-only secondary, or a read-only slave, then you can do read-free replication. Basically what it allows us to do is just turn every single replication event into a message and inject it into the tree. That means dramatically reducing the I/O on your secondary. What it means to you maybe as a system admin is that I have lots more disk bandwidth available for reads if I want to do read scaling on my slaves. Or maybe it means I can use a much less powerful server with less disk behind it for my secondaries now. So it could mean cost savings in either one of 2 ways. But really all these features add up to efficiency of TokuDB. TokuDB in the Fractal Tree itself is all about getting more bang for every single piece of hardware you put into your environment, whether it be more CPU or more disk. Squeeze more juice out of every single lemon you're putting into. That drives down the cost. That's very attractive for people that are in the MySQL and the open source software in general. But here's just a quick summary of some of the things I talked about. You know, the differences in the data structure, B-tree versus Fractal Tree between NoDB and TokuDB. We both support transactions. One thing I didn't talk about that everybody needs to know is that TokuDB doesn't support foreign keys. It hasn't ever really since the beginning of the storage engine, and it probably won't in the future. The reason is that we're a real performance limiter. And we don't find that a lot of people coming to us for performance want to use foreign keys because of the fact they're such a performance limiter. So if you have foreign keys, NoDB is probably your best bet. Compression, we both do compression. If you've ever used it in NoDB, you know it can be a little bit painful. But in TokuDB, it's a lot less painful. Peter will be going into that a little bit in his presentation. Clustered indexes, I already went over it, primary key and NoDB. Any one you want to do in TokuDB is fine with us. We can both do hot schema changes, although TokuDB's hot schema changes require a lot less resources. And if you wanted to think of it simply in terms of strength, in-memory working sets in NoDB are fast, really fast. If you can keep your working set in memory in NoDB, you're doing really well, and you're not going to get better performance from TokuDB. But if you want greater than memory performance that will stay the same as your database scales out, TokuDB is the way to go. That's where the Fractal Tree works best. The weaknesses for NoDB can be efficiency, obviously, especially when we're working outside of memory. And for TokuDB, very small point queries can be a problem because we're on disk in very large chunks. So they can be more expensive than they are in NoDB. But those can be tuned. But really, that's a good sum up, I think, of TokuDB. Up next, Peter's going to show you guys the practical side of what using TokuDB really looks like. Thanks for listening.
Hello. Hey guys, do you hear me? Somebody should say what you hear me.
I hear you.
Okay, wonderful. Just double check. I don't want to be talking for 15 minutes and just then figure out I still am muted somewhere. Yeah, so wonderful. So in my section, I am going to take a practical view, right, why I like energy. There is going to be some overlap with what John has been seeing, but if I hopefully also tell you some of the new things. Now, what does the practical means, right, in this case? Well, you should know what Percona has been running TokuDB in quite demanding production for about 9 months now with our Percona Cloud Tools project. So we have been helping people with some TokuDB installations, but we also have a very first-hand experience of it. And then I also personally invested quite a lot of times looking into it because, well, I like to really understand things if I am to talk about them. Now, it's worth to note what also at Percona we have been working with Tokutek for a long time. Relatively early versions of TokuDB, well before it was open source, where the Tokutek would come to Percona and ask our feedback to do some benchmarks to see what we find working and what's not, what priorities are. And we really have been working with Tokutek quite closely since 2009. Now, my take is what TokuDB is, even though it's relatively new and not as popular yet as in EnergyBe, it's a very solid storage engine. As a Percona, additionally to the work what TokuDB has done, we have done a very extensive QA with TokuDB, as we included that in Percona Server. We found and fixed some bugs, but here we were very happy to see what TokuDB engineering team was very responsive and very smart and able to fix those bugs with very high response time, or very low response time, I mean. And I think that is very important from a practical experience, because chances are, if you're a really heavy technology user, you will find some bugs, and it is important what you are able to get those resolved very effectively. Now, if you look at my global view, I would say what the TokuDB is pretty much the only solid transactional storage engines besides the EnergyBe or the XRB, which is a variant which exists for MySQL. Now, a few things what I like about TokuDB. One is it is close to zero tuning. With EnergyBe and some of that legacy of the old MySQL history, which was supposed to be running in very, very small boxes and not taking a lot of resources, you actually have to tune a significant amount of options like EnergyBe buffer pool size, log file size, enable direct I/O, and few others to get decent performance. Now, TokuDB offers essentially pretty good performance out of a box with no tuning at all, and I think that is very important for some users. It also after tunes for hardware scale is the most important option. So if you have TokuDB and you just give it larger Amazon instance, for example, it will just choose to use the larger caches without anything what's needed to be set. Now, the only variable I think the most users will need to work with is this TokuDB commit sync, which is essentially equivalent to EnergyBe's EnergyBe flash logo TRX commit, and which allows you to trade off between the full ACID durability and kind of delaying the log flashing and doing that periodically instead of at each transactions commit, and getting some extra performance this way. Now, the next thing I wanted to talk about the compression, right? I mean, we know what EnergyBe done. EnergyBe has compression, but I believe what EnergyBe compression is done wrong, right? This is have been done as an afterthought for compression. It's dramatically complicated code, and it was responsible for many bugs in recent MySQL releases. And it also, because it complicates the code, it really impacts performance even if you're not using compression. And additionally to that, because of how it's designed, it has a pretty high performance degradations when you put it in use. Some people are using EnergyBe compression because in some cases it's still better than no compression at all. But honestly, I wish what EnergyBe would never implement compression. I think it would be better storage engine this way, and if somebody needs compression, you could just run the file system with just compression on that level. Now, in TokuDB, on other thing, I think the compression fits very well, and it's kind of compression right. Compression was a very early part of design, and also compression fits very well when you're having relatively large block sizes, right? The larger blocks you can compress, the more compression rate you can expect. Because of this design, which John has explained, we can get a relatively low performance overhead with compression, and at the same time achieve a high level of compression. Now, we have spoken what TokuDB is write optimized, right? When you insert the data in large tables, it can happen that very fast. Now, it's worth to notice what EnergyBe also have some keys when it can do that as well. So, for example, if you don't have any indexes and you just have a primary key, then let's say after increment primary key, then inserting in the end of a table will be very quick as well, because sort of a small portion of a B tree which is active for insertions can be kept in memory. But TokuDB can do that even if you have many indexes. Another trick a lot of people use with EnergyBe is using MySQL partitions. As the same thing applies, if you can just have one hot partition which gets a lot of inserts, then that can give you very good performance if EnergyBe. Well, in TokuDB, it's not required, even though you can use partitioning with EnergyBe as well. Now, at the same time, TokuDB is still rather efficient with reads. As John has mentioned, it's really their case, or the largest penalty comes when you have non-cached point selects, because we have to go to a disk, have relatively large disk read and uncompression. Now there is something else I wanted to talk about efficiency here. John has mentioned about what TokuDB is efficient with updates, because it can just take the message and put that in the buffer, which is going to be in the cache. But if you think about that logically, there are actually two kinds of updates which are very important, very different. One kind of updates is essentially some value replaces, right? If you do an update table sets, column equals to 5, where primary key equals to a certain value. In this case, you don't need to know the old column value to make an update, and indeed we can just put the row in and something in. In other cases, that may be more complex with that. And especially in the with a join query. So we have to be looking at what kind of updates can be optimized this way, and which can't. Now the other thing I wanted to mention is what TokuDB is great for solid state work with SSDs, which it has two very good benefits here. One is can dramatically reduce the amount of space it requires through compressions. And that means what you can use SSD for larger set of workloads, even which would require so much space it would be very expensive to do with EnergyBe storage engine. And it also reduces wear. And what that means is what we often can use lower endurance SSDs, which are cheaper and can get us the same same amount for more space, right, for the same amount. This is an example of how much space costs on SSD, right? I mean, if you're looking some high performance, high quality PCIe, then depending on the vendors, you may be looking somewhere from $3 to $5 per gigabyte. If you're looking for some entry-level SATA SSDs, then right now we are looking at the prices starting $0.50 per gigabyte. So it's getting pretty affordable. Now, even if you are not running with your actual proper physical hardware, and if you're running in the cloud, the same things applies, because obviously the cloud provider will have to pass your costs to them, and the more provisional IOPS, for example, you will have to require, the higher costs are going to be. So as John mentioned, you'll have your benefits here as well. Here are also some prices for endurance, right, I mentioned. And what we're speaking about here is what different solid-state drives, they have a different amount of writes they can handle. So for example, here I'm speaking about the two kind of relatively similar SSDs from Intel, both for 400 gigabytes PCI Express drives, but one of them is certified to sustain 7.3 petabyte of writes, and another costs it can do just 2.2 petabytes. I think what is interesting though is what if you are concerned about how much writes the SSD is able to handle, then more expensive drives are often more efficient, because as you can see from those numbers, you can do more terabytes written per dollar for more expensive variant than less expensive one. At the same time, if you're running something like TokuDB which doesn't require as much writes, you may go for lower cost variant. Now, the next advantage what I have noticed in TokuDB is what EnergyBe actually can suffer pretty badly when you're running long-running queries. And at the same time as heavy writes. Because in this case, EnergyBe may have to create a lot of old raw versions which will be expensive to manage, expensive to clean up for later on, and so on and so forth. Now, TokuDB handles such workloads very well, and what that makes it, in my opinion, is very good for what I would call like semi-real-time analytics. Right, then you are, let's say, inserting and updating the data, and it is not your Hadoop scale when you really want to crunch from a bunch of petabytes of data, but you want to analyze data over a few millions of rows, right, and you want those queries to be the interactive, right, or maybe close to that by periodically updating dashboards. TokuDB can handle this kind of workloads very well. Now, we spoke what that comes essentially from the how MVCC or multi-version concurrently control is implemented. So what is the difference in implementation between TokuDB and EnergyBe? Right? In EnergyBe, MVCC is implemented as having a special area which is called undo space, where all the previous rows are stored, and then there have to be some purge threads and garbage collection process which clean that stuff out. It is actually a decent design for the B tree what the EnergyBe is based on, because it allows you to avoid having amount of garbage or holes in B tree or excessive kind of split and merge operations. But it's not really required for Fractal Tree. The Fractal Tree it's compressed, right, and it's kind of through this message it's can handle many old versions pretty well, as well through inserting those messages and pushing them down. You can keep your cleanup and optimization as a part of a normal operations, which is essentially done when something else is touching the same area and don't introduce a lot of cost. Now, what is very related here is fragmentation, right? What we know with EnergyBe, due to those multi-version implementation, and in generally as data can be updated, deleted rows can be of a different size, you may end up cluster keys and indexes becoming fragmented, and performance can go significantly down compared to your optimized EnergyBe tables. That means you may be looking at doing optimization, like optimized table, every so often. With the TokuDB and Fractal Trees, the need for that is less, because the data structures don't fragment so easily. Finally, let me show you some graphs which I think are very good to illustrate some of the data points. This is, I'm sure, the test you're familiar with, right? It's shown out there in a lot of TokuDB marketing materials, and it shows, hey, if you're looking at 1 billion row insertion tests, it is going to be much faster with TokuDB compared to EnergyBe. Depending on their your hardware, their different versions, numbers can vary, but it's going to be much faster. The other is the compression comparison. That is also the slide I took directly from TokuDB, and we can see in this case what with EnergyBe, typically depending on the block size you take, you can get 2.1 to 4.1 compression if your data is well compressible, while with TokuDB it can be going to be much larger than that. I have mentioned what we are using TokuDB for Percona Cloud Tools project, and in that case we have a compression rate depending on their tables ranging from 5 to 15x, and we're using standard compression, right? So those numbers are not some artificially high numbers. They're in the ballpark of what you would expect. Here is the load speed, right? I think that is a very interesting data in terms of how quickly it takes to load the data for EnergyBe uncompressed and compressed, and indeed TokuDB is both much slower. EnergyBe is much slower to load, right? And in TokuDB there is less gap from either compression or going for more aggressive compression. This is a where graph which I noticed, and let me explain how you understand that. Now, in this case, you can see the graphs end at the different times, right? And this goes through the fact that TokuDB completes these benchmarks much faster. And if you take a look at the difference between number of IOs, what EnergyBe does in average kind of normalized to do the same amount of work, the difference can be 25x. Right now, in this case, I would be careful using exactly that as a difference number, because most likely you'll also have something like a binary logs and some other stuff which will produce a similar amount of writes for EnergyBe and TokuDB, but in the end, I would still expect there is several times difference in amount of writes, and so where which EnergyBe produce. Now, you have seen what this insert benchmarks is really focused on inserts, and I was often joking with TokuDB guys saying, hey guys, I mean, why do you use these benchmarks? You can put a black hole engine will always be faster still, right? You have to show what you can actually read the data quickly as well. And here is a benchmark which Percona does, which is a link benchmark by Facebook, which is kind of somewhat emulates what MySQL workloads they carry. And you can see what, in this case, on a relatively large database, which was, I think, about 1.2 terabytes in size, we get EnergyBe is significantly slower than TokuDB still. And what is also especially interesting, what if you tune EnergyBe for this workload using a smaller EnergyBe TokuDB read block size, provides a substantially better improvements. Now, in this case, it would be worth to note what it is not just about the B3, which showed this pretty tremendous gap between EnergyBe and TokuDB, but also the index 3 contention. EnergyBe has something this EnergyBe index lock, right, which really prevents concurrent modifications of a single index tree, which this benchmark really puts in a heavy use. So just so you know. Now, there are some benchmarks I did run over the last couple of days. Number of updates, right? And this is you can see this is something about one sysbench of 10 million row, right, and Pareto distributions, and you can see what the numbers are: about 400 for EnergyBe and 160 for EnergyBe compressed, where it is more than 6,000 and more than 3,000 for TokuDB uncompressed and compressed. And this is happens because with the pure updates, TokuDB is able to push them very well in fractal trees and not really hit the disks as heavily as EnergyBe. And I was actually surprised by those results. I didn't think the difference would be that large. Now, another benchmark that I have done is doing the full table scan query. Again, the same sysbench table, and we can see in this case how badly EnergyBe compression impacts the scan speed. Right, we can see what when it comes to uncompressed EnergyBe, it's actually can scan, do the full table scan from disk relatively efficiency, while it becomes very inefficient with compression. And what we can see in this case is what compressed TokuDB does a full table scan from the disk or on this hardware with approximately the same speed as EnergyBe uncompressed. Now, what is also interesting about this workload is what this is a workload which is designed to be not compressible very much. Right? You can see for this specific side there, EnergyBe, which is able to compress data about 2x, is almost the same size as TokuDB compressed, which is, I would say, an exceptional more of an error. What I also find quite interesting here is what uncompressed EnergyBe is actually takes quite a lot of space. Right, you can see what it takes even more than EnergyBe. This is kind of just a theoretical exercise, in my opinion, because it is very unlikely you will need to use completely uncompressed TokuDB for something. Now, let me kind of finish this off by talking about the comparison of TokuDB versus EnergyBe. Now, in my opinion, what EnergyBe is absolutely great storage engines, which I was using successfully for many years, and it has really proven track records. Facebook, Twitter, Google has proved that you can run reliable applications at the large scale of EnergyBe. There is also a lot of experience operating and tuning EnergyBe, right? You can just Google essentially any question about EnergyBe and find a lot of matches. So that all makes EnergyBe a really great default choice as your database. So I'm not suggesting you to say, hey guys, you know what, go ahead and replace your EnergyBe storage engine of TokuDB without even looking, and it will just have everything wonderful. What I would suggest is if you have a demanding applications where you're looking for performance and scale, efficiency, right, or reducing hardware costs, then it makes sense for you to explore and evaluate TokuDB, and it may be just a very good fit for your application. If you are looking for some more resources, I would would suggest you to download and explore Percona Server with 5.6. And there's also great resources both on the Percona website and TokuDB, Tokutek about TokuDB. Now, in terms of Percona, we are happy to provide support, consulting, managing services for users deploying, evaluating, or having deployed EnergyBe. Contact us through website, email, phone. We would like to talk to you. And I also wanted to invite you to Percona Live MySQL Conference and Expo, which takes place in Santa Clara in April. Two things you need to know. One is that the early birds ends in a couple of days, so it's a great time to get a great prices for tickets. And what we are also still looking for speaker proposals now for Birds of Feather session and lightning talks. If you think you can contribute something, please suggest one. Thank you. That's all for me.
Okay, now we will turn the floor over to Tushar Katarki.
Thank you, Peter.
Go ahead, Tushar.
Okay, thank you, Alison. Thank you, Peter. This is Tushar Katarki, and I work at Percona in product management. And I wanted to thank both the speakers and the panelists today, Peter Zaitsev and John Tobin, for an excellent overview of both the technology as well as practical tips and practical aspects behind Toku and our experiences here at Percona. With that, I'd like to, there are several questions that we have received, and we have about 5 minutes. So what I'll do is I'll try to pick a few which I find a common thread in, and I'm going to ask them, and then the rest of the ones that we may not be able to answer in the next 5 minutes, we will try to follow that up with a blog post. So if you have more questions, feel free to ask, and if we can't get to it, we'll follow that up in a follow-up blog post. So the first question really is, is about the TokuDB installation, and either John or Peter, you can answer this. But starting with John, what is the largest TokuDB installation that you have dealt with, John?
The largest one that I know of is a customer of ours that has, at last I knew, I believe it was 110 billion rows. So pretty large installation, but I have to assume Percona Cloud Tools is going to eclipse that before too long.
Peter, do you want to add anything to it?
Yeah, well, I think that's about right. I mean, I would maybe even have a question to John. Do you know, in terms of a number of data, how much data are people able to feed to the single server with TokuDB?
Are you talking about in terms of inserts per second, Peter,
no,
or are you talking
just about like terabytes, right? I mean,
yeah.
Of data.
I think that use case is a little bit over 2 terabytes uncompressed and roughly about 600 gigs compressed, but don't exactly quote me on that.
Okay. Thank you, guys. So let me move on to another question here. One of the questions that has come up really is, in general, how does, the two-part question. One is, if you use MySQL or Percona Server with TokuDB, can you use replication, the various replication schemes? And a follow-up to that really specifically is, how does is performance impacted by any of the replication?
Okay, John, do you want to answer? I think you should go first, and I'll comment if there's something to add.
Yeah, sure. So in theory, MySQL is actually what controls the replication in MySQL. So as a storage engine, replication is not impacted by TokuDB. However, I did explain a little bit about read-free replication. So that can help you increase the performance of your slaves in your environment, and you can certainly run in a mixed environment with DB or ExtraDB as the primary and TokuDB on your slave. Go ahead, Peter.
Yeah. Okay. Yeah, thanks. I just want to comment what for Percona Cloud Tools specifically. Very careful, right, deploying new technology. And what we have done first is we would set up TokuDB on the slave, right, and replication from EnergyBe to TokuDB worked perfectly. Then we flip that over, and then we run TokuDB on the master and having some EnergyBe as a slave in case something goes wrong, right, and that worked that direction as well. And I think so. It's A, it does work cross storage engines. B, I think that can be a very good tool for migration path, for safe migration path for TokuDB.
Great, fantastic. I think that there are several questions in that direction, so that's good to know. Now switching gears a little bit, I think there is a question here on the support for TokuDB. Does Percona support, gold, platinum support for TokuDB? And maybe I will answer that since I'm the product manager. And the quick answer to that really is yes, we have what is known as an add-on support for Percona Server for TokuDB, and you'll find more details on the resources page that, like if you go back a couple of slides, Peter, you will see that exact page right there that Peter is showing actually has details of it. Okay, let me see. So one of the other questions that has come up really is Galera clustering, well, Percona HDB cluster, does any of that support TokuDB right now? And the short answer to that really, and let me answer that, is not yet. Right now, the initial release, basically here we are supporting Percona Server, but that's certainly something that we are looking at. Peter, you want to add something to it?
Yeah, I mean, I would say it would be right to say what we support EnergyBe storage engine, right, in the Percona Server cluster. That's what focused on, right. In general, the Galera replication technology can support TokuDB storage engine, right. And if that's something you would like to see, let us know. And if there is good demand for this kind of technology, then we can consider building it.
Okay. Let me see. So there is a question on does TokuDB use a single table space or one per table? Is this configurable with something similar to EnergyBe underscore file per table?
Well, yeah, let me answer this one. So, no, in the TokuDB does not have any configuration in this regard. What it does is it would use several files for each of the tables, like one file per index. And what is also different about TokuDB as it is right now is what it doesn't held those files in a database directories. They are all stored in the same directory, which defaults to their MySQL database path. I think that is something what a possibility for change and improvement.
Cool. I know that we have reached the end of the 1 hour mark, so there were a few more questions, but we'll try to follow that up separately in a blog post, as I said. With that, I'll thank again Peter and John, and hand the mic back to Alyssa, so to speak.
Hello there. Thank you so much, guys. It was a great webinar. Audience, I want to thank you for attending. We do have several more questions, and like Tushar said, I will send them over to Peter and John for them to address. In addition, everyone will get a link to this recording and to the slides, so that should be coming within the next 24 to 48 hours. And I'd like to thank you again for attending today's webinar, and I hope that you have a great evening, morning, afternoon, wherever you're calling in from. Thanks again, everybody.